Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And we have a trio today. And I am very happy to have Francis Rigby, Lorenzo Pica-Ciamarra, and Nikku Madhusudhan with us today. Hello, Francis, Lorenzo, and Madhu.
Hi,
Frank.
Francis, let's start with you. What's your geolocation? Where are you at?
I'm in Cambridge at the moment in the UK.
All right, cool. Is there snow on the ground? Does the UK get snow?
No, not much snow, just cold,
Oh,
cold and a
cool.
bit windy. Yeah.
Okay. Okay. Very cool. Francis, excuse me, Lorenzo, you have a very awesome, what is that, a light? Is that a painting over your
Yeah,
shop?
well, it is a light. It is a light which kind of looks like a starry sky. So I
Yeah,
thought it would be
yeah,
a good thing for this
yeah.
chat.
Yeah, it looks like one of those universe maps where, they flatten out the
Yeah,
universe. They put all on it. It's
I,
very
I
cool.
don't think it's accurate. I don't think it's an accurate depiction of the constellations, but it's quite beautiful anyway. So
Very cool. Very cool. And Madhu, how about you? Where are you at?
I'm at Cambridge as well. I'm in my office right now.
Okay. And Francis and Lorenzo, you both graduate students?
Yeah.
Yes.
Cool. And Francis, when will you finish up?
This year, I'm final year at the moment. Yeah.
Well, let me be the first to congratulate Dr. Rigby.
Not quite
Very
yet, but thank you.
very
Close
soon.
enough. And how about you, Lorenzo? When do you finish up?
Well, I'm in my second year now, so I
Okay.
do have quite some time ahead of me.
Okay.
I think February 2027 is my deadline. So I
Very
have
cool.
like a couple of years and a bit more than that in front of
Very
me.
cool. Very cool. And Madhu, let's go with you first. What do you like to do for research?
My team works on a wide range of things related to exoplanets in general. We work on atmospheres, we work on interiors, habitability. In the past, we also worked on connecting atmospheric compositions to their formation, and so on and so forth. So we do a lot of atmospheric characterization these days, both on the observational side and also theoretical side. So we do a lot of JWST observations of um, sub-Neptune planets, especially temperate sub-Neptunes. And then we try to use those observations to understand what atmospheric processes, internal structures are possible with these planets. And yeah,
Very
and
cool.
considerations of habitability as well.
So the proverbial double threat here of observationalist and theorist. Now all you got to do is design some experiments, some instruments, and you can be an instrumentalist
That's
too.
it.
It would be awesome. There you
We'll
go.
cover the full suit. Yeah.
All righty. And Francis, Dr. Rigby, what do you like to do for research?
So I mostly look at the interiors of sub-Neptunes, also interested in atmospheres and habitability in sort of a smaller sense.
Hmm.
So yeah, most of my time is spent on theory, so doing internal structure modeling, trying to relate observable properties of exoplanets to their internal composition, their surface conditions, that sort
Yeah,
of thing.
hot topic these days. Absolutely. And Lorenzo, how about you? What do you like to do for research?
Yeah, so I mostly work on the atmosphere side of things. Every once in a while, I take a look at interiors, but that's not really my area. Mostly interiors as well, but I think I enjoy playing with observations whenever the chance arises.
Very
And
cool.
mostly habitability is what I find really interesting. So that's my area specifically.
Nice. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Toward a self-consistent evaluation of gas dwarf scenarios for temperate sub-Neptunes. And Francis, Lorenzo, and Madhu, take us away.
Hi, yeah, thanks, Frank. First of all, I would like to thank all the authors. You see, we have a big team there with a wide range of expertise. So I would like to thank all our co-authors who are not here at this moment, but have contributed substantially to this work.
Good shout
Uh,
out. Good shout out.
and, and yeah, so this work is, I mean, the origin of this work is from the first JWST observations of a temperate sub-Neptune that we just published last year. So if you have that plot up that I mentioned uh,
Sure.
earlier, let's see if we
Sure.
can get that plot up.
Give me 1 second because Zoom is a little silly on this. So boom. and then we go back to here, and then we go back to share, and we will take a look at this spectrum that came out last year on K218b.
Yeah, so K218b is a sub-Neptune. It's about 2.5 times Earth radius and about 9 times Earth mass. And it sits in the habitable zone of its host star. But conventionally, you wouldn't call this kind of a planet to be habitable if you're used to thinking about Earth-like planets, because it's big for that. But if years ago, we had proposed this concept of Hycean worlds, where planets can be significantly larger than Earth, and still be habitable, because these kinds of the Hycean worlds, the word Hycean comes from hydrogen and ocean. What they are ocean worlds with thin hydrogen-rich atmospheres that can allow habitable conditions on the surface.
Cool.
So K218b, it was the poster child for that as a candidate. So last year we published this spectrum, which was the first spectrum of a habitable zone sub-Neptune. And you can see all those features. And the big takeaway from this was that we detected methane and CO2 at very high confidence. But we also put constraints on their chemical abundances. We measured about 1% roughly of methane and carbon dioxide. But importantly, we also didn't detect other molecules which you would expect. If it's a deep atmosphere like that of Neptune, you would expect methane, you would expect ammonia and carbon monoxide, which we did not detect.
Okay.
So this is where our story started last year. And this spectrum launched a lot of activity in the field in the direction of how do we understand these objects, because there are no such planets in the solar system in the sub-Neptune regime.
Yes.
Between Earth and Neptune, there are no planets in that size range in the solar system. So what are these is the big question.
Right. Very cool. And I will put a link to this article in the description below the video, so people can go back.
So if we go back to our present paper,
and
what happened?
Zoom silliness. Okay. And we go back to here, and one more share, and away we go. Okay.
Yeah. So with that observation, what happened was that we know for sure that it's a hydrogen-rich atmosphere, and we know its rough chemical composition as I just described.
Okay.
The problem is that there is a degeneracy in internal structures, in the sense that several different types of planets could explain the bulk parameters of the planet with a hydrogen-rich atmosphere. Okay. So for example, you could have a Hycean world, like we were talking about, an ocean world with a thin hydrogen-rich atmosphere.
Right.
But you could also have a mini Neptune, which is a smaller version of Neptune with a deep hydrogen-rich atmosphere and an icy mantle and a rocky core.
Okay.
You can also have a third alternative, which is a gas dwarf, which is a rocky core,
yes,
a rocky interior with a thick hydrogen-rich atmosphere. All these three internal structures are degenerate if you just take the bulk parameters, the mass and radius.
Right.
Now the big question in the field is, can you use the atmospheric abundances to break that degeneracy between these three internal structures?
Good. Okay.
In my group, we work on all these possibilities, and we try to predict what chemical compositions you can see, and if they agree with what we are observing. So this study focuses on the gas dwarf scenario. The rocky interior with deep hydrogen-rich atmospheres.
Yes.
Now, why is that important? It's not important just because of these observations. There is also a background to it, in the sense that gas dwarfs have been proposed as a possible explanation for the radius valley.
Yes.
So the sub-Neptune radius valley is basically the distribution of planetary radii between 1 to 4 Earth radii, and there's a bimodal distribution with 2 peaks at 1.8, but there are 2 peaks, one centered around 1.4 micron, another at around 2.4 micron.
Okay.
So what is causing that distribution is still in debate.
Yes.
There are multiple hypotheses. One invoking ocean worlds for the larger objects and like rocky planets for the smaller objects. But then there's another hypothesis which says that the larger objects they come from a common population with thick hydrogen-rich atmospheres, gas dwarfs,
Okay.
but that smaller population has lost most of that, and the larger population has retained much of that envelope.
Fair enough. Okay.
So I mean, these are competing hypotheses.
Mm-hmm.
So observations of their atmospheres are essential to establish if the larger population we're talking about are actually gas dwarfs.
Yes. Yes.
In other words, can you look at their atmospheric compositions and say that these are planets with a rocky core and a thick hydrogen-rich atmosphere? That might explain the larger population in the bimodal distribution.
Cool. I'm with you. Mm-hmm.
So that's one motivation for that. Now, if you scroll down, so we discuss all of this in the introduction, and this spectrum of K218b basically kickstarted that journey
Cool.
of trying to use the atmospheric observations to finally being able to say something about their interiors.
Yes. Cool. Okay.
So that is our basically poster child right now for all these surface atmosphere interaction experiments, theoretical experiments, if you will. That was the first one. And since there is at least one other planet that has come up with similar observations.
Okay.
So then in this particular study, we decided to look into this problem. And I should mention that this is not new. Attempting to use atmospheric observations or making predictions for atmospheric observations of gas dwarfs have been happening in the field for a few years now.
Yes.
So there are several studies I list down there which have made different kinds of predictions for what you would see for a gas dwarf. So in this study, we decided to do we basically decided to do a self-consistent modeling exercise, both on the planet side, but also try to use that to explain the observations, which previous studies have attempted, but not in a fully self-consistent manner. We can discuss this further, but this is basically the most self-consistent modeling, if you will, that has been done to date in this domain. And we tried, and that was motivated by the quality of the observations we had.
Nice. Very cool.
Cool. So it's an integrated framework basically for temperate sub-Neptunes to explain those observations. So now we can dive right into the paper if you're ready.
I am ready.
Okay, let's go.
I understood that one perfectly well. Okay, methods. Let's get into it. Structure and
Cool.
composition.
So methods. So the best part to get a big picture view is figure 1, actually.
Okay, let's get figure 1 methods. Here we go. Here's the integrated framework.
Yeah, so that's our flow chart for the various components that are involved. When you do this kind of modeling, what happens is that you start with basically what constraints have you got. So we have mass and radius bulk parameter measurements.
Okay.
We have atmospheric observations, as we just discussed.
Right.
So those are our observables. And then we want to see what are all the physical processes in the atmosphere and interior that could work together to affect the bulk parameters that you're seeing.
Okay.
So that's the big picture. So what we did is to reverse engineer that process by saying, well, let's first use the bulk parameters, do the atmospheric structure modeling based on the atmospheric abundances and constraints we have in general. And then once you model the atmosphere, this flowchart goes with the cartoon in figure 2, as you can see. So you model the top atmosphere first, and then the observable atmosphere, and then you model the deep atmosphere, which is that H2 rich, most of that H2 rich envelope that Francis is going to talk about. And then you model the interior, and then model the surface atmosphere interactions, see what chemistry happens there, and then you propagate it backwards and see how that chemistry will affect your observable atmospheric composition. So if you go down that flowchart, that's what it's doing. Basically, we start with atmospheric structure, we do internal structure modeling, and then we go deeper and deeper and come back up again into the observable composition. So we're going to, so now I'm going to pass this on to Francis, who will talk about the internal structure and magma surface, the surface of the potential magma surface, or basically the surface of the rocky part, whether it's molten or not. And then Lorenzo is going to take it forward from there and see what happens within those surface atmosphere interactions and how do they affect the upper atmosphere. And then I'll come back again to explain the observable consequences.
Cool.
I will say at this point that studies have attempted to do this in various ways. Not specifically for, one study did it specifically for this planet, but other studies have also predicted such things. So we are really building up on concepts that previous studies have introduced, but we are doing it in a more integrated framework in this paper. So just take it away.
Cool.
Yeah, so thank you, Madhu. That was such a good summary. It's lovely to hear. So yeah, I'm going to talk about the internal structure side of this, which is clearly the sort of second major step in our integrated framework. And the internal structure modeling is really, really crucial, because if you just consider your sort of magma atmosphere interface just on its own, you might be using surface conditions that aren't then consistent with the bulk density of the planet. So what you have to do is take into account the mass and the radius, therefore the density of the planet, when you're actually modeling these surface conditions. So they've all got to be consistent. And that's what we're doing in this step of the modeling.
Very cool.
Yeah, so to do this, we use a code called HIRIS, which we outlined in our paper previously this year. Early this year. Yeah, just checking I've got the date right. So in its most basic form, an internal structure model relates observable properties of an exoplanet. So usually it's mass, its radius, then some kind of information about the atmosphere. And it's going to relate that to what the interior is made of, in what proportions. So in this specific case, if we're looking at K218b, we have its mass and its radius. Then what we can do is we can vary the proportions of different layers in the planet. So if you wouldn't mind scrolling back up to our little sort of pizza slice of planet, figure 2. So this will just show the different layers that I'm talking about. Yeah, fantastic. So you can see we've got 3 layers that we're considering. So we've got our iron core in the center, then our silicate mantle, and then our hydrogen-rich envelope. And each of these layers is described by an equation of state, which is just the density varying as a function of pressure and temperature. I won't go into this in too much detail because there's a lot of detail there.
Yeah, EOSs have a tendency to do that. Yes, they do.
Yeah, they definitely do. So the one thing I will say is that for the silicate mantle, we're assuming this to be peridotite, which is a common mantle mineral. So then what we can do, we've got our mass, we've got our radius. We also have these outputs from the atmospheric structure modeling. So this is the pressure temperature profile in this hydrogen-rich envelope at the top. These go into the model. We vary the fractions of the silica and iron in the core. And then what we get is the mass fractions of each layer. And then overall, if that matches the radius, we know that that's the solution to our particular planet. I think the easiest way to then see this might be table 1. If you mind scrolling down to that for me.
Let's take a look at table 1 here briefly for a second.
Further down than you think it is.
Yep, it's all good.
Buried.
Okay, very good.
Fantastic.
This is for K218b, and away we go. Okay, I'm with you.
Yeah, so like I say, we vary the mass fractions of within the planet to try and figure this out. And particularly, we're going to be varying the content of silicate. So each case that we're looking at, we have a pressure temperature profile in our atmosphere. We have a percentage of silicate versus iron in our interior. And then for these 2 specified things, for the mass and radius, we're going to get one value for the interior mass fraction, and we're going to get one value for our envelope mass fraction. So those are our results, essentially. Then what we can get from that is our conditions at the surface. So given these mass fractions, we then specify this has to be the pressure and temperature at the surface for this pressure temperature profile in our atmosphere.
And what are the
really important?
What are the essential differences between the various C1, C2, etc.?
Yeah, so actually, let's scroll down to figure 5 if that's okay.
Sorry, I didn't mean to push on that. I was just
no. Yeah.
Figure 5. Okay, let's go to figure 5 and let's figure out what C1, C2s are. Okay, here we go.
Yeah, so C1 to C4, these are our different profiles, and we're varying parameters to do with the hazes, and we're varying the internal temperature as well. So you can see we've got C1, which is our coldest, and C4, which is the hottest.
Thank you. Good, I'm with you. Okay.
Yeah, and then so on the y-axis, we've got our pressure, which is obviously increasing as we go further down the y-axis. So we're going deeper into the atmosphere or the interior. And
Yes.
then on the x-axis, we've got our temperature.
Okay.
In the background, what we're showing is the sort of the solid and liquid phases of our silicates.
Uh-huh.
So what we can do is when we have our surface conditions, which is the sort of black dots along the line,
Uh-huh.
um, we can see whether this is going to be in the liquid phase or the solid phase.
Okay.
And if it's the liquid phase, that's going to indicate that we could potentially have magma. If
Correct.
it's the solid
Okay.
phase, probably not going to be magma at the surface.
Okay. I'm with you. Gibbs free energy. Love it. Okay. Mm-hmm.
So
Right.
yeah, that's probably the most important thing to come out of my step of the modeling. So the two really key parameters that we get are the surface pressure and the melt mass fraction. So if we have a liquid, so molten surface, we can also calculate the fraction of the planet that's actually going to be in this molten phase, which is this X melt parameter that we've got in this column here. And those get fed on to the next step of the modeling, which Lorenzo is going to talk to us about.
Yeah, some of these get kind of large, up into the 10, 12% ranges for the
Yeah.
HOTS models.
We will come back to this in our results section.
Okay.
Yeah.
It's quite a thick melt there. Yeah. Okay, cool. Okay, I'm with you. What's our CD?
Yeah. So if we go back to our flowchart, figure 1.
Okay, just slurping down some abundances here, seeing out. Okay. Let's zoom out a little bit and go back to our flow chart. And there we go. Okay.
So should I take it up from here then, I guess? Francis just wonderfully explained the top half, maybe, of this chart and got us to the question of are there feasible magma surface on the planet?
Yes, right here.
And if you can scroll back to figure 5, if you don't mind, or actually table 1 is even better.
Okay, so magma, not a magma, is a magma. Okay, figure 5, I'm with you. And figure 5.
Or table 1 is actually better. Table 1 is, oh, what happened?
I don't know. Hang on one sec. Let me get this back.
Too much scrolling
Let
happening.
me get this back. Let me get this back. Okay, technical difficulty, all good. Okay, I didn't plan on this. Open recent, there we go. 2023, 2024. And dang it. Sorry about this.
No worries.
What happened was the article decided to close itself. So I'm going to have to go back to here. Oh my goodness. This is taking much longer than I want. We might do a little clip on the this.
Okay, so I can put this in the chat if you like, the link.
Yeah, I'm good. Just give me one sec.
Okay.
For some reason. Okay. We are back.
Okay, great. And we can go to it's gotten narrower somehow.
Yeah.
Okay, yeah.
We had a technical glitch there, as it's known. Sorry about that. Figure 5. Okay.
Or table 1 if you don't mind.
Table 1. Okay.
That's clearer. Yeah, perfect. So as you can see here, we have 2 classes of solutions. We have 4 out of the 12 cases we're considering, which end up in having no melt at all. And in that case, it's quite easy what we do. We just have an inert surface, which isn't really doing anything from a chemistry point of view, if not just stopping the atmosphere at a given pressure.
Yes.
And so what we do there is we just look at what happens in terms of thermochemical equilibrium at the bottom of the atmosphere.
Okay.
So we have the temperature and pressure conditions, which are the result of Francis's model together with the PT profiles.
Yes.
And after those, we can just infer what are the equilibrium abundances of relevant species. And of course, deep down in the atmosphere, equilibrium is all that we really care about for chemistry, and so aren't that significant once you get to 10 to the 5 bar or that order of magnitude.
Yes.
So that's the starting point when we just have no magma. In the cases, though, where we do have magma, and those are a significant part of our cases, we need to add something on top of that. And what we need to add is the solubility of this species in magma. Because,
Oh, yeah, that's right. Yeah, yeah.
of course, when you have a lot of, say, N2 nitrogen in the atmosphere, or of any other significantly present species in the atmosphere, then that will in part go into the magma, and it will be partitioned between the magma and the atmosphere according to how soluble each of these species is in the. And something that we realized while working on this is it's not quite as straightforward as there being a constant as so much as partition. There's a very significant dependence on the temperature, the pressure especially, and also the properties of the magma. So for the properties of the magma, as Francis said, we assume periodicity. So that's something that we are keeping fixed. But then as you can see, we have a wide range of temperature and pressure. And if you can scroll down figure, I think it was figure 6, perhaps.
6. Let's go down to figure 6, and there we go. Fugacities.
So what we have here is that we're just putting one of the cases, a representative one, where we are showing what is the impact in this specific case, which is when you have a 30% silicate in the atmosphere with the C3 profile, which is one of our more warmer ones.
Okay.
We're showing the impact of the solubility on the abundance of these volatiles on the left on the species and on the elements on the right.
Okay.
So as you can see, crucial parameter here is what we call oxygen fugacity, which is basically the partial pressure of oxygen at the bottom of the atmosphere, corrected for non-ideality effects. In this case, we're assuming ideal behavior of oxygen and of all gases, so it's really just the partial pressure of O2 at the bottom of the atmosphere.
I'm with you.
And our self-consistent calculation with equilibrium chemistry in the atmosphere and solubility and equilibrating all of that gives us a range of what we can expect this partial pressure to be, which is highlighted in gray in the two panels.
Yes.
And we can read off the significant impact that the solubility has on the abundance of these volatiles. So for example, if you look at ammonia on the left, that is the purple line, you can see we have a decrease in this one case of about a couple orders of magnitude.
Oh, yeah.
Compared with the no melt case, which is the dashed one. In the dashed one, we are assuming no solubility at all. So it's quite significant.
Oh, that's quite significant, yeah. Mm-hmm.
Not that significant for others. So if you look, for example, at carbon monoxide, CO, the black line, in that case, there is no difference.
Yeah, very small. Very small, that one.
Of course, what we care about is not really the species, because the species vary depending on where you are in the atmosphere. You know, if you go to lower pressure or in the temperature changes with that, the same elements will be partitioned into different species.
Yes.
So what we care about is actually what happens in terms of elemental depletion when you introduce some solubility. And that's what you can see on the right. So the line you can see, the dashed black line, you can see there, is where we're starting off for all elements compared to hydrogen. So that's just 50 times solar abundance. And if we had no melt, that's where we would be at. There would be no change respect to that black line.
Yes, I'm with you.
What is happening though is, as you can see, we do have some significant departures from that, especially when it comes to nitrogen, but also when it comes to sulfur. And of course, with the oxygen, you see that, but that's kind of a given because we are plotting these as a function of how much oxygen is in the atmosphere. So of course, it's a given that we have this kind of trajectory. But what we can see is there are significant elements, significant impacts in terms of abundances. And so once we get for the cases with the melt, you can see we are plotting two lines, a solid one and a dotted one. And the dotted one is showing what happens if you multiply the melt fraction by 2. So compared to what we have in our actual case, or to what the self-consistent calculation is giving us, we're just saying, okay, what if it's twice as much? And that's just to get an idea of how significant the melt fraction can have of an impact on the depletion. As you can see, it's not very strong. It doesn't change that much. It's a factor maybe of 2 or at most. or so. So that's not very important. It's a linear dependency on the depletion and the meltdown.
Okay. Okay.
So,
And just one question on these plots. You got two gray bands. What do those gray bands mean?
the gray bands I mentioned before is where we expect to be given our calculation on this x-axis. So the x-axis is how much oxygen you have at the bottom, and the gray area is telling us what we think are the realistic values at the bottom of the atmosphere for that variable.
Thank you.
Once we know how much nitrogen, carbon, oxygen, sulfur is there in the atmosphere.
Yes.
The next step is seeing what happens to these elements. So what we do is we want to understand how the bottom of the atmosphere impacts the top of it. And so to do that, the first thing we have to do is looking at what happens in terms of equilibrium chemistry,
Yes.
which is the most important thing at the bottom. And for the very lowest part of the atmosphere, we just assume efficient mixing, which is given by the fact that it's going to be a convective region, because the temperature is such that it will be convective. And so we assume efficient mixing. So we assume these elemental ratios don't really change compared to the very bottom of the atmosphere for like the bottom part of it.
Okay.
And then on top of that, we look at what happens with thermochemical equilibrium, which is just what you would expect if there were no other processes happening. And then on top of that, and that is very significant for the uppermost part of the atmosphere, you can go to figure 7 for that. Figure 7, yes.
Okay. Yeah, here we go. Vertical profiles. Okay.
So what you get is, and you can see the dashed lines is what happens if you only consider thermochemical equilibrium, and the solid lines is what happens if you also consider photochemistry and dynamics.
Quite a difference.
So as you can see, the bottom of the atmosphere doesn't really change much for the very lowest part, but as you go further up, it does have very significant impacts. And this way, that's how we can get the observable abundances of the different species in the atmosphere. And that's, if you look at the region which is shaded in gray over here, that's a range of pressures that we think we are observing at. And so that's where we should compare our model outputs in terms of abundances for all of these species with our observations. And so if you, as you can see here, on the left-hand side, we have something which shows a case with no melt, and right-hand side we have a case with some melt. And you can see there are significant differences. Look, for example, at ammonia. But if you scroll
if I may interrupt here, I think we should come back to the results.
I was saying don't go back to table one. Table one. Yeah, I was about to say that.
Go on, finish what you're saying, but then
but I just wanted to go back to table one now. I was saying the same thing. I just wanted to where all this goes to, but I want to go back to table one, and then we can look at this in more detail later on. I just wanted to give a full outline of why we care about elemental ratios at the bottom of the atmosphere. The reason we care about that is because on the last 4 columns of the table, you have the elemental ratios that result from our melt calculations. And I think the most important column here is the N over H column, the nitrogen over hydrogen abundance. And as you can see, in the no melt cases, we have a log ratio of minus 2.47, which is just 50 times solar. But then, depending on the melt presence and pressure, there is a very strong dependency on pressure.
Absolutely.
We arrive at different depletions of nitrogen over hydrogen. But overall, it's not a guaranteed. I think that's one of the most interesting things that are coming out of this paper. It's not that having some melt, even significant melt, leads to a lot of nitrogen depletion. If you look at the C3 case for 100% silicate, you have a ton of melt there. You have 11.9% is going to be in the melt.
Yeah, it's a lot.
But you get not even 1 of nitrogen depletion. Well, if you look still at the C3 case and the 5% silicate case, in that instance, you have much less melt, 2.6%, but you get almost 4 orders of magnitude of depletion in nitrogen. And for that is the very, very strong pressure dependency of nitrogen solubility in the melt. So overall, here to explain our observations we need a couple of orders of magnitude to get something which of depletion, to get something which is just about consistent with our 2 sigma upper limit on the abundance of ammonia. And so we would need N over H to be at most minus 4.5. And you see that's actually quite tricky to get. So if you look at the cases where we're assuming what we think is the most likely interior composition, that is 67% of the interior is going to be in silicates. That's what we have on the Earth.
Okay.
Of the 4 cases we're looking at here, 67% of the interior in silicates, only one of these cases gives us enough nitrogen depletion to just about explain our observations. And that's the C1 case, the third row in the C1 case. Otherwise, if you want to look at more extreme scenarios as well, say only 5% of the interior is in silicates, and by the way, we think that's an extremely unrealistic scenario, but we want to for it just for completeness, but we don't see how that could happen. It would be extremely surprising if that were to happen. In that, if you expand it to those kind of scenarios, you do get a few more cases with melt, but still only 5 out of 12. So I think that's the really key insight that we have out of here, is that, yes, you can get some nitrogen depletion, but not that much of it.
Yes.
So and for the other chemicals, for the other elements, carbon is barely changed at all. Oxygen has really changed that much, neither does sulfur. Sulfur does have some departures. If you look at the C3 100%, minus 4.1. But not very strong. And also, we don't really know with great confidence how the solubility of sulfur-bearing compounds, especially H2S, which is abundant at the bottom of the atmosphere, works. So we don't, these are, for sulfur, it's interesting, but we are not really stressing that point. So now, as I said before, we have all the elemental abundances. We know how to evolve them to the upper atmosphere. And so at this point, I think we're ready to talk about the results of this and the observable composition this yields, which I think Madhu will walk us through.
Cool.
Yeah. So if we go back to our top figure, just move around the figure 1. Yeah.
Yeah.
Yeah. So what Lorenzo just explained, so I just want to bring it all together. Francis went from the atmosphere and basically calculate what the boundary conditions are at the surface of the rocky part, which in my view is the most critical aspect of this entire scheme, because that is what drives whether or not you have surface atmosphere interactions. Right. So, and then as Lorenzo mentioned, depending on the pressure temperature conditions that Francis provides for a given PT profile, you'll have to do the surface chemistry with or without melt to see what the elemental conditions are. So so you go down that arrow, and if there is no magma surface, then you have an inert surface, and then you come back to do equilibrium chemistry. If you have melt, you go through that other loop and do the magma-atmosphere interface and so on. And then you do all of that and come to the very bottom box, which is the non-equilibrium chemistry, which you have to do in the upper atmosphere for the observable part. And then that predicts the observable composition. And that is the one you compare with the retrieved abundances. So this is
Sepctra that we looked at.
So now we go to section 3, where we've developed this model, but you want to know, is this model right? So
that would be useful.
Exactly. So we compared. Section 3 is about validation with previous results. So we compared it. Comparisons with previous work. So this framework is generic enough that you should be able to use it for rocky planets, terrestrial atmospheres. In this particular study, we used it for like a K2-18b like planet, a hydrogen-rich atmosphere. But in principle, you should be able to use it for like smaller planets also. I mean, currently we're assuming hydrogen-rich atmosphere. But we have done that for several case studies, and we basically, the summary is that we agree with what previous work has done. I want to keep it at that for the terrestrial atmospheres. And then if section, I think the next subsection is what 3.2 is for 3.2.
Sub-Neptunes with H2 rich.
Exactly. So this is the new bit, which a few studies have done it in the past, where they've predicted what you would expect for gas dwarfs with H2 rich atmospheres, and there were some characteristic predictions, like you expect more CO than CO2 and so on. So along those lines, studies have predicted. But most recently, there was another study which looked at the specific case of K218b
Okay.
and also tried to explain the abundance. And one of their conclusion is that you could potentially explain it with this gas dwarf scenario, the lack of ammonia
Okay.
scenario. So we looked at that in great detail because we have the observations and this is the planet we work on. This was very important for us.
Sure.
So we looked at it. The summary of that entire section is that currently it is very difficult to explain all the abundances that we are seeing with the gas dwarf scenario. And then we'll come to this in the results section again. But what we did is basically see exactly what the assumptions were in previous models. And we found that because those models weren't fully self-consistent in the sense that they were assuming what sort of melt fractions, they were parameterizing basically the amount of melt you have.
Parameter survey. Yeah.
It's fine, just a parameter scanning.
Yeah.
They did get some solutions that could explain is what they said, but then when we looked at it, we found that those would violate your mass and density constraints.
Okay.
So it won't work. So that is what motivated us to actually go ahead and do the self-consistent, like fully integrated modeling framework. Then, I mean, there are always more improvements we can do in the modeling. We can come towards the end. But in our when we do this integrated modeling framework, we found that actually it doesn't explain all the abundances. So that's all that I want to say about comparisons with previous work. And finally, now we can go into the results section and this is what we find.
Table 1's been a favorite, so it's figure 5. Let's slide down to 4 on K2.
Francis, do you want to say anything on the magma side of things, either comparison with previous work or in the results section?
I suppose from the results section, the most important thing to stress is the fact that the surface pressure is such an important parameter that then feeds into the atmosphere chemistry. And the surface pressure is then highly dependent on your atmospheric temperature structure and the proportion of silicates that you have in the interior. So as Lorenzo mentioned, we explore some very extreme cases of 100% silica in the interior and only 5% silica in the interior, both of which are probably quite unlikely.
And members, let's call them.
Yeah, that's a good way to phrase it. So I think that's what I would want to stress, that these parameters are all very dependent on each other.
Okay.
So here in the results section, what we have done is that we went through that flow chart, the atmospheric modeling to begin with, the structure modeling, then the interior modeling, then the melt modeling at the
really no figure 1. Yes.
And then come back up. Right. So each of these subsections are going through each of those parts. So 4.1 is just the atmospheric structure, very standard. We have used self-consistent models to generate those PT profiles that Francis showed at the very beginning. The C1 to C4 PT profiles, and that's what gives you the temperature structure in the hydrogen envelope at the top, and then the internal structure. Do you want to say anything about section 4.2? Francis?
I think I would be repeating myself if I did. I think I've given my key results.
Oh, you can never say it enough. You can never say it. It's all good.
So she had already showed you the results in table 1, basically, that when you explore those temperature profiles across the board, what she has done is we have 4 temperature profiles, and for each temperature profile, as Francis just mentioned, we consider different bulk material fractions. For example, 100% silicate interior, or an Earth-like silicate interior with 67% silicate, or more denser and denser compositions like 30% silicate, the rest being in iron, or 0.5%. So this is all the permutations and combinations. It comes to about what, like 12-ish compositions we have tried. And for each of that, you get these calculations of surface pressure and temperature, and then in this section here, we are talking about what the range of those surface conditions
The
are
gray bars in the plots, yeah.
and the pressure and
Okay.
temperature conditions
Oh,
at the
okay.
boundary. And this is why Francis was emphasizing is that perhaps the most important thing that comes out from all of this
Boundary.
is the surface pressure, I would say.
Yes.
Um,
It's a boundary
and
condition on the atmosphere.
it's the boundary condition, lower boundary condition for the atmosphere, but also the upper boundary condition for the rock surface,
Oh, yeah.
whether you have melt or not. And that also drives Lorenzo's part, where it drives whether or not you have significant solubility.
Yes.
Yeah.
Yes.
So if we go to
Yeah.
4.3,
surface is important.
4.3, Lorenzo already talked about that at length, what the abundances you expect based on that. Is there anything more you would like to add, Lorenzo, at this point?
Not that I can think of on this time. The only thing I will point out is that if people who are watching this are interested in knowing more about the details of the solubility laws that we're using, etc., we have a whole Appendix A on that, and they can have a look at. Especially when I mentioned that we are not really sure about sulfur and the pressure dependency of nitrogen, all of that. We have quite a long section on that with some plots and a table on Appendix A. Just if you're interested.
It's in a beautiful appendix. People go check it out.
Yes. So yeah, so I would like to here give a shout out to again to all our co-authors. I mean, the three of us are talking, but a lot of people were involved in
Yes.
this whole effort on all aspects of that
Yes.
of that flowchart we were talking about.
Cool. Good.
Cool. So if we go down to wrap up the results part, so Lorenzo went into great detail about the abundances. So the figure that's just at the top of this page,
Yep.
which is basically once you get the surface conditions from the internal structure modeling and then do the solubility calculations and surface atmosphere interactions, the end result of that is elemental abundances at the bottom of your atmosphere, of your envelope. Right now you have a thick hydrogen envelope on top of this rocky interior. And as Lorenzo already discussed, these melt atmosphere or the surface atmosphere interactions are only giving you the elemental abundances at that interface.
Yes.
But you need to know how those partition into molecules in the observable atmosphere all the way at the top at about a millibar level.
Yes.
Right. So for some part of the atmosphere, you assume them to be well mixed. Some of it is convective, and then you have vertical mixing and so on. But then eventually you'll run into photochemical processes, kinetic processes. And that is where the section 4.4 comes in. So we go ahead and then do the photochemistry for these elemental abundances that you get from the surface atmosphere interactions. And then that is what gives you the molecules that you should see in the atmosphere.
Yes.
So if we go to the figure that's coming up, I think it's figure 8.
Figure 8, we should see.
Figure 7. Okay, no, we can stay here at figure 7 first.
Figure 7? Okay, sorry. Figure 7. We'll look at these verticals again.
Yeah, so we got here. So that bottom is at 10 to the 4 bar. That is close to your surface. It can be slightly higher pressures, but then you'd see that all the solid lines are the predicted abundances as a function of pressure. And then the points with error bars or upper limits are the derived abundances from the spectrum. Okay. So this is one case. I think this is one of the higher melt cases where you do see on the right hand side, for example, you do see ammonia depletion. Right, so that is consistent with the upper limit, but we chose that's by design. We chose the case to show the case that has the depletion.
Yes.
Quite strong. But most of the cases that is not necessarily the case. Okay, so for example, if you assumed an Earth-like interior with 67% silicate, there is only 1 out of 4 cases where you can just about borderline depletion.
Okay. Yes.
Which was seen. And then the other cases that actually match do need like very high iron fractions or very low silicate fractions. But that is only half the story as far as matching with abundances is concerned, because you'll see across the board here that the CO2 abundances predicted, which is the gray curves,
yes,
the gray curves are significantly below the gray data point.
Okay.
And that is the problem.
Yes. Yikes.
Right? So even if you could force all the parameters that we are using to get you just the right amount of ammonia depletion, you'd
Yes.
still be way off on the CO2
Right.
mixing ratio.
Which is way.
And more importantly, it's the CO over CO2 or vice versa, the CO2 over CO fraction
Ratio,
that
yeah.
is also important, because you'll see that in all those cases, the prediction is that the CO is more abundant, the black curves is more abundant than CO2.
Yes, it is. Black, gray, black, gray. Yes, I'm with you.
And that is opposite to what you see in the data.
Yikes.
Okay. So these are some of the problems you have with this scenario. Now, I must say that this had been pointed out in the literature before. So, I mean, this part is not new. People have done simple calculations which say that you need to have more CO than CO2 in a gas dwarf scenario. And even the ammonia depletion concept is not new. It's been like a few years ago, 4 or 5 years ago, people had already said that if you had a reduced mantle, you can have ammonia, nitrogen depletion. So none of these concepts are new.
Yeah.
But like it's only recently that people are trying to use them in different ways to explain observations.
Right.
And when the previous study tried that, they were one step where they did one part of the problem, but they hadn't done it like self-consistently. So they ended up violating the mass and density constraints and the CO2 over CO ratio. So all I'm trying to say here is that when you do this integrated framework, these sorts of things come to surface. That's the advantage of this approach, is that you begin to see where
your holes are.
where the model falls apart or where it explains things.
Right.
So I think that's the big picture. Now, finally, if we go to the last figure, like figure 8, how does that show up in your spectrum?
Yes.
How does it show up in your spectrum? So the top panel is showing the contributions of the various molecules to a fiducial spectrum that you can get from these compositions. And here what's happening is that all these molecules that you have in the atmosphere, you do a radiative transfer calculation to derive what is known as the transit spectrum, which is what we observed, right? So those data points are what we saw at the beginning of this session.
Yes.
And the black curve is the model.
Got it.
And you'll see that it can explain some of the peaks, which are due to methane. We saw in our chemistry plot, figure 7, that methane is abundant because of this deep atmosphere. But you see that it doesn't really match between 4 to 5 micron, where you expect a carbon dioxide feature.
Yikes. Okay. Yep.
And that is because of what you saw in the chemistry plot of your model being very low in CO2.
Yes. Yes.
Okay. So that's the gist of it. This is how it all comes back together. We do exercise caution that this is not the right way to compare to observations, because this is just one model, and to compare this, you have to do it in a more statistically robust manner. So we rely more on taking the observations, extracting the chemical abundances from it, and then comparing the chemical outputs of the model to those abundances.
Yes, almost in reverse. Yeah.
Yes. Yeah. So to us, like that's the more more reliable way.
So it's almost an inverse problem, so to speak. Yes.
Exactly. So that's the big picture.
Very cool.
Doing here.
Very cool. Beautiful. Beautiful work. Francis, Lorenzo, and Madhu, I want to thank you so much for walking us through your very awesome article. Nice.
Thank you. Can I, if you go to the summary of the paper, we can talk about the summary very briefly, but I want to highlight points for the viewers to take away. Is that we are right now, we are living in a really revolutionary time with like JWST, that we can even have this discussion with this observation. So I want to take away like
theorist.
I want people to take away like 2 key points. I mean, people can read this paper in great detail, a lot of information here, but there are really only like two things I want to highlight. One is that we know these objects are complex and they have no analogs in the solar system.
Correct.
Which means we need to put every effort possible to try to build integrated frameworks which can address all the constraints we've got.
Right.
So we have mass radius constraints, we have atmospheric observations, and so on. So
Mhm.
as much as possible, we have to look at it in a holistic manner, put all the observations together, put as many theoretical components together for the whole planet as one whole, rather than doing piecemeal, to get a consistent picture. Otherwise, we could end up making like inferences that are not really justified or violate key,
Right.
key aspects like mass balance, as simple as that, right?
Well, that would be
So that's one thing, and the second thing is what we had already talked about, and Lorenzo mentioned in very good detail, which is that the concept of elemental depletions in magma had been around for a while.
Yeah.
So it's very tempting to use one element here, one element there to say, oh, if we see an element there, it should be this. It's very tempting to do that, but it's important to explore the parameter space in a realistic manner.
Right.
And what we find in that case is that it's not guaranteed that you have a magma just because you have a large planet
Doesn't
and a
mean
big
that one.
atmosphere, you'll have a magma. That is not a given. That's what Francis's calculations show.
Right.
In several of the cases, you don't have a magma. Just because the atmosphere is hot doesn't guarantee you a magma either. Because if your atmosphere is hot, it will be extended and your pressure will be low. That means it may not be molten as well.
Okay.
So all these parameters would say that just because you have a gas flow doesn't mean there is a melt. And just because it's a melt doesn't mean that there is depletion of a given element. So we have to remember like these sorts of things. There are some cases where we can explain depletions, but it's not a universal thing. So we just want to leave it there in the sense that we should be open and explore all possibilities, but let's do it in a self-consistent manner,
Fair
given
enough.
the data we're getting.
Fair enough.
Anything you might want to add, Francis and Lorenzo?
I think you've summarized it very well. So no, I don't think I have anything to add.
I agree, and I think you made a very good point of making it very clear how we do need to make sure everything works together because it's one planet at the end. We're simulating, and a planet has so much.
Well, that's true. At the end of the day, it is one.
Yeah, it's not several different. It's one planet.
It's like doing Monte Carlo on a specific. There's only one object, right? So okay, very cool, very cool. So Francis and Lorenzo and Madhu, I want to thank you so much for walking us through your very awesome article.
Oh, thank you.
And you kind of hinted at it there a little bit toward the end. And so let me go ahead and push on it a little bit. And where do you think we go from here, given the published work? So what would be some of the next steps, some of the future near-term steps that might occur? Are there more parameters to study in a given model? Are there perhaps holes in the model that one would like to fill? One, of course, would always like to have better EOS data, better solubility data, etc. Are there other systems where you could apply this technique to? So just sort of next steps, where do we go over the next couple of years?
Yeah, no, you said it. The main things you already said it, which is, and this was just a first attempt at an integrated model, and I'm sure our colleagues in the field are also trying to do that, and it's good we do that across the board. But there are some fundamental things missing. Solubility data that you mentioned, EOS data, and reduced mantles are not very well studied because the Earth isn't one, right?
Yeah, right.
And so how do you get solubility data for very reduced mantles is a big open question, and that's
If I may add on that.
Yeah,
If I may add on that, the thing is,
please.
we can reduce mantle, it's one thing, but here we're not just dealing with reduced mantle, we are dealing with a mantle which is very reduced, very high pressure, and rather high temperature. So it's three things which make this mantle very different from anything we're used to on Earth. So getting studies that looked at solubility when all of these three conditions applied was hard to find them. And there is definitely a need for people to look into that further and give us more precise and more advanced data on that.
Yeah, so let me push on that. So some of that I would imagine could be done in terrestrial experiments. like, put it in a diamond anvil and get your pressure right and get your composition right, go ahead. So, is there some experimental work that could be done to help improve the situation?
Yeah, I mean, it has to be done experimentally. The diamond anvil typically is for material equations of state, but what you also want to create is a reduced environment for that material to get the material properties, and that is going to be the difficult part.
That makes that a little harder. I only want a diamond anvil on part of it. Not all of it.
And like solubility, equation of state is one thing.
Yeah.
You also want like the solubility properties for like different gases. We're talking about like all these gases that we mentioned, the sulfur-based, nitrogen-based, carbon oxygen-based, and so on. So that. And Frances again did great job on the internal structure model. So her code, the high-risk code, which we use for internal structure, we just published earlier this year in another paper.
Cool.
But obviously there can be more enhancements to that as well, to the internal structure model, and how we do the melt calculations for different materials and so forth. Is there anything you want to add on top of that?
Yeah, for me, it's equation of state data at those high pressures for the relevant mantle minerals is the big one.
Yeah, and for us, as we mentioned, yes, solubility, that's the big problem. Again, most of the data, yes, it's experimental. There is some computational simulations, molecular dynamics, and all that, but the vast majority of the data we do have is experimental. And again, it's hard to get the relevant conditions in experiments.
Right.
Yeah. Cool. I would like to thank my team for this heroic effort. Lorenzo actually got all that solubility data into in the appendix that you're seeing, collected all of that, and another of my former student, Mons Holmberg, did all the solubility, like the equilibrium calculations, and Savas, another of my student, did the photochemical calculations, and we have several great collaborators aiding on each of those steps. So it is really like a big team effort. But I think we can take a lot of lessons from these on all those aspects where improvements can be made in future studies. You asked about more data. There is definitely more data coming for several of these sub-Neptunes over the next a lot more data. And those will be our testing grounds for all these theoretical models. So I think we are entering a very rich regime of planetary science here. It's going to be.
Yeah, it'll be really exciting to see this develop over the next couple of years. It'll be really great.
Really
great. Very nice. Frances, Lorenzo, Madhu, thank you once again.
Yeah, thank you. Thank you very much for having us on here.
Yeah, and that'll do. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Thank you. Bye, everyone.
Thank you. Bye.